Thanks. So we hear a lot these days about a clean energy economy. And one of the big bottlenecks to achieving this clean energy economy is actually materials development. If you think about solar PV and you read the industry news for solar PV, a lot of it is about finding new materials that are low cost and very efficient that would beat traditional silicon. If you read industry news for electric vehicles, a huge amount of it is about finding a battery, finding new battery materials that allow you to drive for 200 miles without a recharge. So a lot of these industries are really waiting for better materials before they can really ramp up commercialization and realize this clean energy economy. One of the big problems is that it actually takes 2 decades to commercialize new materials. So materials development is really slow. What this chart shows is the average time it took to go from invention to commercialization for lots of different types of materials. So the first example is lithium-ion batteries. Those were invented in 1976, but they weren't commercialized until 1991 or 15 years later. And that was largely due to materials problems with the anode. And if you look at lots of different types of materials, semiconductors, you look at metals, it always takes about 20 years to bring them from the lab to the market. And this is a big problem given the urgency of the clean energy problem. So what is it that causes this large delay in materials development? We really think that it's a lack of materials information. So if you're a materials researcher, you're this orange person, there's a lot of things that you don't know that you need to guess. For example, what are the properties of known materials? There are about 100,000 known materials, inorganic materials, but the properties of most of them aren't known. So if you have a certain material and you want to know its band gap so you can design a solar cell out of it, you have to guess what it is because no one's done the experiments. Or if you want to know the bulk modulus so you can make a structural material out of it, you have to kind of guess because there's no experiments on it. So that's kind of a big problem that makes designing new materials very difficult. The other thing is that there's 100,000 known materials, but there's all sorts of new materials that might exist that people don't know about. And the way that usually you find them is that you take chemicals from the lab, you take a little bit of iron oxide, a little bit of lithium oxide, you mix them together and you see what happens. And most of the time nothing happens and you waste your experiment and you do this over months and finally you find something new. So people really need guidance on what kinds of new materials could exist. And then finally there's this problem of simultaneous optimization, which is when you design a material in your head without any prior information, you typically optimize just one property. So if you're designing a solar cell material, you say, how can I make it really efficient? But when you actually commercialize materials, a lot of things need to be in place at the same time. It needs to be, if it's a solar cell material, it needs to be in the sun for a long time without degrading. If it's a battery material, you need to be able to cycle it many times without it degrading. So there's all these other things that you don't necessarily optimize for in the first round, but then they come back to bite you later. So right now, experience is the only guide that lets you, design materials, and that's really slowing down the process. So the big idea that we had was to use computations to generate materials information. And the type of computation we do is called density functional theory. It's based on quantum mechanics. But basically, you take your material, which is a bunch of atoms in a box, and you throw them in a computer, and the computer solves the equations, and you get some materials properties out. You don't get all the materials properties, but you get lots of important materials properties out. And typically, for one of these materials, a typical one will take about 1 day on about 8 to 16 cores. So they're not huge computations, they're not super small computations either. The big thing, though, is that computation is scalable. So if you have twice as many computers, you can do twice as many computations. And if you have 3 times as many computers, you can do 3 times as many computations. And so basically, this is what we did. We scaled this using a high throughput method, massively serial jobs where we have tons and tons of jobs, and we've run this now for hundreds of thousands of materials. And the big question we wanted to ask is, well, we have all this materials data now that were generated computationally. If you give them to researchers, what will happen? Will we get new materials? So I'm really going to talk about 2 topics. The first one is about lithium-ion batteries, and the second one is this idea that we have of a materials genome. So a lithium-ion battery, everyone's familiar with them. You have them in your laptop. It has 3 main components: the anode, the electrolyte, and the cathode. The anode and the cathode are solid components, and the electrolyte is usually a liquid. And lithium ions shuttle between the anode and the cathode. You can think of the anode and the cathode kind of like a hotel, and the lithiums are like guests that kind of migrate in and out as you cycle the battery. And the electrons go through the external circuit and do work. This talk focuses on the cathode. It's basically what we think is the major barrier to get better energy density. That means when you charge the material, how long does it last? How long does your laptop last on one charge? And also to lowering the cost. So when you think about the cathode material, you can kind of think of it like a lithium sponge. You need to be able to basically, on a microscopic scale, absorb the lithium and then release it, and do this many times without degrading at all. This needs to happen very quickly so that you can charge and discharge in a reasonable amount of times. It needs to be cost-effective and safe. And finally, it needs to be light and compact, especially if you put it in a car. You can't have the entire car be your battery. And this highly absorbent, what this means is you want to have a cathode that really wants lithium to go inside that cathode and nowhere else. Just like for a sponge, you want the water to be sucked up from the floor, wherever it is, into the sponge. You want this lithium cathode to really want lithium inside of it. So most cathode materials look something like this. There's some amount of lithium in it, and that's the source of lithium ions. There's a metal. And the metal is, the job of the metal is that when you have a current in the battery, it accepts the electron or it releases the electron as you charge or discharge it. And then there's some sort of anion group that we call it, which is the structural framework and gives charge neutrality. So this anion group really builds the framework of the material. So before I called it like a hotel, that would set where the walls are and where the ceilings are, and that sets how the lithium ions can enter and exit the material. So what kinds of properties can we compute about batteries for all these different cathodes that we try? There's a lot of different things that we can compute. Things like voltage, which tells you how much energy you get per lithium that you transfer. Theoretical capacity, which tells you for this chemistry, how many lithiums can you transfer. The more lithiums you can transfer, the more energy you can get per charge. Other things too, like safety and how fast you can charge and discharge. So what I'll show you now is a movie, and what this will show is the progress of our computations. And every single point that you'll see is one material that we've computed, one of those cathode chemistries. Some of them are previously known, and some of them are ones that we've kind of just tested in the lab, ones that we've tested computationally, just very virtually. So every frame is 1 month of computing, and each of these orange dots is a new material that we've computed for that month. And for a commercial, this just stopped. Okay, so for a commercial cathode material, you really need to be between 3 and 4.5 volts, and you need to have a capacity of about 150 milliamp hours per gram or higher. So what we see is that there's a lot of materials that have the right voltage and that have the right capacity, which will give you a good energy density. But a lot of these materials actually won't work. And this actually comes down to that problem I said before about simultaneous optimization. You need materials that are also safe, that are going to cycle very well, and all these other things. So we actually need to evaluate those other things for these points as well. But at the end of about a few years of computing, we've screened about 13,000 cathode materials, which is much more than you could usually do with experiments. So we have all this information. We have information on 13,000 different compounds. Does it actually lead to better materials for lithium-ion batteries? And so far, we've found 3 materials. These are the compositions of the 3 materials that are new for batteries and that we think will actually have the potential to make impact. This first material is actually one that's already known. People had known about this composition, lithium manganese borate, but no one had tested it as a battery before. And that's actually a common thing. People are finding materials all the time that are useful for batteries, but that were known for decades or even more. The second group of compounds, lithium metal phosphocarbonates, that's a completely new chemistry that we predicted with our computation, and then one of the experimentalists actually made it in the lab, and they were actually finding that it has good battery properties as well. This last one I'll talk about in a little bit more detail. It's a lithium vanadium pyrophosphate phosphate. I actually took about 6 months of my research to learn experiments and then learn how to synthesize things. And I actually found a synthesis route to this material, so I made it in the lab and actually characterize it electrochemically as well. And all these things have the potential to be improved over current commercial cathode materials. So this one that I was working on, this lithium, vanadium, pyrophosphate, phosphate, the picture to the right is what it looks like. The green atoms are lithium, the blue atoms are the metal groups, and then the purple atoms are the phosphate groups. And basically what this curve shows if you're an electrochemist is that this thing is cycling. Each one of these curves is one discharge and one charge. So it's actually working as a battery. But it's about 65% there. If it was 100% there, you could actually commercialize this thing. And we were working on ways to improve its properties, but then this happened. I got scooped. Another research group actually found the same material just by experimental methods, and they published it before I did. So that was fun. But we have more ideas on how to actually make this material even better. I was doing more computations, and we're finding that actually if you substitute some metal into this material, this is the original material, the properties that we predict, and this is after you substitute the metal. There's actually one substitution that works really well. So going back to this question, if you have all this information, does it lead to materials? Sorry. You have all this information, you can pick out materials, but can you actually learn things that are new? We picked out 3 materials from that list of 13,000. We have this large data set. Can we learn new things? And one thing we can learn something new about is safety. Cathodes can be unsafe if they release oxygen gas. If they release oxygen gas, that can interact with the electrolyte and cause fires through thermal combustion. So this is what you don't want to happen. And this is something that we can compute along with the voltage. And one thing we found, each of these points is one of our computations. We found that as you increase the voltage, you actually increase oxygen partial pressure, which is worse safety. So higher voltages, less safety. So this is one design constraint that materials designers have that they didn't really know about when designing new cathodes. You can't just increase the voltage, it decreases your safety. But each of these different subplots tell you a different anion group. Remember, that was the last part of the cathode. And depending on the anion group you choose, you can actually get different voltage versus safety behaviors. So you can actually break this down more and say for a particular metal and for a particular anion group, which are these circles, what kind of voltage can I expect? What kind of safety can I expect? And you can make these plots that show, okay, here are the anion groups, here are the metals, and the orange ones are the ones that give you both high voltage and high safety, and the other ones just don't work. So when you have all this data, you can actually, it's not that much resources. It's one research group, 300 computing cores, but you can screen tons of cathode materials and find new design principles. And this is a project that's still going on. So I just really want to quickly talk about this idea of a materials genome, and the goal is to really do what we did for batteries, but allow other people to have access to the data and use it for their own applications. So there's an alpha version online now. If you have a computer open, you can go to materialsgenome.org and stuff will show up. We have a lot of different apps that material scientists can use for designing materials. We have this, for example, this reaction calculator where you can get 20,000 different computed reaction energies. In experiments, there's probably like 2,000 or 3,000 that are known. You could use this, for example, for designing CO2 capture materials. We've used it in the past to design mercury sorbent materials for pollutant sorbents for coal gasification. And there's these other tools, too, that you can use. One of the things on the site is a list of materials that we predicted from our computations but have never been seen before. So those experimentalists that are just mixing things randomly in the lab can have an idea of what things might actually exist. So one of the things that we put online was a tin titanium oxide ilmenite structure, and actually a different research group was able to grow this as a thin film, and they cited our paper on this as having found it before. And we have about 200 of these predictions. We're actually thinking about having a contest and saying, here are our predictions. Whoever can synthesize the most of these predictions gets money or something. We're still working out the details. This is our usage. We just basically went online June 2011. We have 24 new users in that month. We have about 50 total so far. You can actually use the website without being a user. So the users are the people that really want to use the website very heavily. People computed 138 reaction energies. It computed 363 phase diagrams. This is the first month that it's been online. We expect these numbers to go up in the future. So just a few concluding remarks. The first one is that the amount of computation needed to do this isn't that big. To do 50,000 computations, which will get you through most of the materials that are known in nature so far, requires something like 15 million CPU hours, which is big, but it's not huge. If you have a good grant to buy your own computing clusters, which is what we did, it takes about a few years to go through all these materials. if you had NERSC Hopper for 4 days, you could do all of it. But of course, you would never run massively serial jobs on Hopper. But the raw computing power is there. It's really, we don't have machines to do these massively serial jobs or these high throughput jobs on this sort of 15 million CPU hour scale. The second remark is more like an advertisement, but one group won't solve the problem. It started at MIT. We're now collaborating with Berkeley Lab, and also the University of Kentucky is donating computing. So if you're at all interested in this project, we're very much looking for collaborators. So this is what we hope. If you're a materials designer, that will give you tools, and you'll design materials that will change the world. Thank you.